All right. The next thing we want to look at for rotational kinematics is in terms of remembering there's one little catch that we have to worry about with things moving in a circle. So if something moves around a circle, then it's at the same location in space whenever you go one time around. So if you start here and you go around, then you are at the same physical spot whenever your angle position is not the same value. So every multiple of 2 pi radians, you end up at the same location. So in some types of problems, you may have to end up being careful that the angle position may be different whenever your physical location is the same. So I gave an example, and we suppose we've got a point that's on some rotating disk. It's initially moving at 1.75 radians per second when it passes by a so on a merry-go-round. That if it's speeding up at 0.72 rads per second squared, we want to find out the next time it passes the tree. So we spin around like this. We got a tree sitting over here. So it passes by once. It speeds up going around the loop. So we want to find out when it reaches the tree the next time. And the trick is, even though the place is the same, your angular position has gone up by 2 pi. So it's 2 pi radians and not 0, even though it's the same geometric place. So again, it's one of those things, it's subtle, and it's not that hard if you end up thinking about it the right way, but bear that in mind. That may come up in computations. So in order to end up solving that, we again go back to our rotational big four. And in this situation, we have, we know what our initial angular velocity is. We know what our angular acceleration is. And we know what our change in angle is. So, and we're looking for our time. So in that situation, we look for the one that connects those together. And remember that angular position corresponds to position. Angular velocity corresponds to velocity. Angular acceleration corresponds to acceleration. Of course, time corresponds to time. So we look for the one that connects the things that we already know. And then we end up shifting it to angle variables. And so we end up writing out the equation. And again, your change in angle there was 2 pi. We were not slowing down, we're speeding up our motion, so we can end up choosing, starting, for example, from 0 position, we end up at 2 pi at the end. Then both our angular velocity and my angular acceleration are both positive. So then we end up plugging into our formula, and then we use the quadratic equation, same old way we've done before. One of the things that does come up a little bit more often, I've seen it on some things you've done computationally in the past. Make sure when you type in something like 2 pi on a calculator that you put the 2 pi in parentheses, because if you type let's say a number divide 2 pi and you don't have parentheses, your calculator is dead stupid. Your calculator is not smart. It's efficient, but it's not smart. So whenever it does it, it reads from right to left. So it says number times number divide by 2, then times that. It doesn't know it should be 2 times pi on the bottom. So it does divide by 2, then multiply that number by pi, not divide it by pi is what you're wanting it to do. So in this particular problem, the 2 pi is in the numerator, but it is something that comes up from time to time, and some of you made that error on exams before, so I did want to point it out. So you end up going through, you do your arithmetic, and you find that the positive root, which is of course the one that we're looking for, is at 2.40 seconds. You get a negative root 2, which doesn't scan. You can also end up combining linear units with rotational information by using, again, those conversions we had at the beginning. So your S equals r theta, v equals r omega, tangential acceleration equals r alpha. So if you have one of those, you can calculate the other. So our example I gave was a merry-go-round with a radius of 2.40 meters is pushed by a person holding the outer edge of the merry-go-round's handles. So if the person was moving at 7.40 meters per second, whenever you let go, then it takes 18 seconds for it to stop. We want to find the number of revolutions the merry-go-round makes in that process. And again, it will end up slowing down, and we'll end up talking about in the next set of stuff, it will end up being a constant torque, so it will be a constant angular acceleration. In any of these types of problems, if it's not going to involve a collision, so we'll talk about angular collisions a little later, if it doesn't involve a collision, you can pretty much count on it being a constant angular acceleration. So I'm not going to throw something out there that is intentionally trying to confuse you. So in that situation, we end up taking advantage then of how we know what our initial linear velocity is. We know my final is going to be 0 because it's coming to rest. We know the time. So what we have to do then is find what my initial angular velocity is, and we need to find what my change in angle is. So in that situation, we use v equals r omega to find what my initial angular velocity is. So you divide your v by your r, and you find in that 3.08 meter radians per second. Then we use one of our big four. So that's probably the second equation out of the list. But again, on your exam, mainly because of the way this stuff ends up having to work anyway, I'm going to end up letting you use an equation sheet. And what I have in the past, what I've been doing on the other exams, I was going to give you just a sheet. The way it's going to work here, I'm going to end up giving you an exam that will end up being on our homework software, and you can end up you can write your own equation sheet. So whatever list of equations you want, now if you write down 4 pages of equations, then you will still have a 2-hour limit. But so if you're flip, you try to find where this equation is. Oh, there's this really neat special one that does that, and I know it was somewhere in here somewhere, and you spend all your time hunting down some obscure already solved equation. It's better for you to end up doing it a systematic approach. So you can do what you do, but that would be my suggestion. So, but anyway, we use our angular big four, solve for the number of radians, which is, of course, if we put radians in, we get radians out. We're asked for revolutions, so then we end up converting from radians to revolutions. And do make sure, if you type that in your calculator, that you end up getting a number that is the 4.42. If you get some number that's about 40 something, you didn't type it in your calculator right. Make sure when you end up dividing by 2 pi, you put the 2 pi in parentheses. All right. So then what we will end up doing in the next one, we've talked about rotational kinematics. So we're going to end up talking about rotational dynamics in the first one for next week. We'll introduce torque, and we'll introduce moment of inertia, because we're going to introduce effectively Newton's second law for rotation. And so that will be our next major topic.